Okay, so before we go on to the problem number 7, I just want to make sure that we're all clear on how this is sort of playing out. So what we're saying is, if we have some potential energy because of something resting at some height that it can fall, and if it then falls all the way that it can, all of that potential energy is going to be converted into kinetic energy. And these two values, based on the conservation of energy, have to be equal. Now, if we put in our equations for potential energy and kinetic energy, as I said before, you notice that there is a mass on each side. And because we're talking about the same object traveling or going from rest in potential energy to motion in kinetic energy, obviously that mass in each particular situation will always be constant. So the mass is always going to disappear. So what we're left with is essentially two variables, one for height and one for velocity. And what we can do then is solve this equation for each of those two variables. And this will, or should, help make it a little bit easier when you're trying to work through your problem. So let's start off solving for the height variable. So at this point, if we solve what we have left for height, we're just going to divide both sides by the acceleration due to gravity. And so that tells us that when we're looking at these sorts of conversions, the height should just be 1/2 of the velocity squared divided by the acceleration due to gravity. So here, if we have something that's already moving, and we want to know how high off the ground can it get before it stops, before that kinetic energy is all converted into potential, this is that maximum height. So this would probably be a good equation to put down in on your note card. Now we can do the same thing and look at, let's go with this color. We can do the same thing for the velocity and solve the equation for velocity. So if we solve for v squared, we are going to get gravity times height divided by 1/2, which is the same thing as saying doubling the gravity times the height. But that's v squared, so really we have to take the square root of both sides. And we get v is equal to the square root of twice the acceleration due to gravity times the height that the object can fall. So these two equations, then really are ones that you would like to put on your note cards most likely and have handy. Because if we have, in this situation, we have a known potential energy or a known height, and we want to know how fast it's going to be going if it falls that entire height, we can calculate that very quickly using this equation right here. If, on the other hand, we have something moving at a known velocity, we want to see how high it would reach before it stopped, we could use this equation. So if we look at the next, here is a situation where we have a known height, and we want to know how fast is it going at the bottom. So all we have to do is use this equation, the one in teal here, and solve that to find what the velocity is going to be. Okay, sorry about the weird ending on that last slide. I was trying to toggle back and forth between slides, and it does not record in a consistent manner, so we've got kind of a weird ending on that one. But as I was saying there, here is our next problem, and it is one where we have a known height. Sorry about that. We've got a known height, and it's asking how fast will it be going at the bottom when it lands. Now this problem is actually slightly more tricky than it might have initially appeared, but let's go ahead and do the part that we've been sort of focusing on. So if we go back to our equation that we had used, or I had identified on the last slide, we should be able to figure out, in terms of the potential to kinetic energy transfer, how fast it's going based on this equation. So in the vertical direction, the velocity should be twice the acceleration due to gravity, 9.8 meters per second squared, times the height of 500 meters. Now, the only reason that this problem is a little tricky, perhaps, is because this velocity is only talking about in the vertical direction. So this velocity, and it should come out to be at 2 sig figs 99 meters per second, is what you would have simply if you dropped an object from complete rest and let it fall 500 meters. But remember, it also had a horizontal component of 45 meters per second. So it was actually traveling horizontally in addition to falling vertically. So to actually find our overall total velocity, we have got to solve one of our favorite little vector triangles here. Now the nice thing is we're still looking at a right triangle. We have 2 of the 3 sides, so we should be able to find the third side by using Pythagorean theorem. Simple, done. I'll give you a couple of minutes to do that. Okay, problem 8 is actually a little trickier than it might have initially looked. And so we're going to just talk about it briefly, just try to follow along. You do not have to complete this problem to hand in the worksheet and get credit. But I wanted to point out essentially how it's going to work. It is another conversion problem. It is another one where it's saying, okay, as this rope swings down, it's going to actually reach a point that is lower horizontally than it was when it was all the way up. And so the question becomes, what is that height drop? If we know how far it drops, then we can just plug into our velocity equation what that height is and solve for the velocity. So it's easy in terms of what we need to do. The problem is, how do we figure out what that height difference is? How much that height changed? We know that the length of the rope is 8 meters. So when it's hanging straight down, we know that it's hanging down a distance of 8 meters, right? That's pretty straightforward. However, when it's at an angle, it's not hanging down the same length because the 8 meters is now angled off to this side. So what we're going to have to do is create a calculation, a triangle, to determine when the rope swing is swung out to the angle of 30 degrees, what is this new vertical distance that is measuring how far down we are from the top of the tree. If we think about it, if this is 8 meters, and this is essentially going to create a right triangle for us, then we've got a side adjacent to the angle. So this is our adjacent side. And with that, we should be able to find this side very easily using the law of cosine, or sorry, just our general 90-degree cosine rule. So we know that the cosine of the angle is the adjacent side divided by the hypotenuse. So if we want to find the adjacent side, it is the hypotenuse times the cosine of the angle. And we know that the height, or the hypotenuse, is 8 meters. The angle is 30 degrees. So we can solve what our vertical distance is when the rope swing is swung all the way out. If we simply subtract that from our original 8 meter height, that is what determines how much our height has changed. And by using that, you can go ahead and solve for the velocity. So if you want to do that one quickly, it's worth a point of extra credit. Otherwise, please make sure everything is complete on this. pass it over to the usual place, and you will be receiving a new worksheet. I would like you to work through these first 6 problems on the new worksheet. They are essentially the same things that we've been doing here already. It's just a little bit more practice. Miss McKinnon should be able to help you out if you have any questions. She is a retired engineer, so this sort of stuff is simple for her. So she can help you out. Good luck.